Hi, everyone. My name is Alec, and I'm excited to present our paper, which is called Self-Supervised Edge Detection Reconstruction for Topology-Informed 3D Axon Segmentation and Centerline Detection. Over 1 billion people suffer from neurological diseases worldwide, and it can be challenging to develop optimal drugs or treatments for these disorders. And that's simply because we don't have a complete understanding of how our brain functions. One way we can potentially fill our gaps in understanding is through brain mapping, which is the process of connecting or mapping out connections between neurons in a brain. And these connections are known as axons. And domain experts can manually trace axons themselves, but this is very time and labor intensive. So this is not practical for large-scale brain mapping. People have looked for ways to perform automatic brain mapping instead, using machine learning and specifically deep learning methods. In particular, the 3D UNet architecture has achieved great performance in this axon tracing task. But the downside is, in order to train a UNet, you need a sufficient amount of annotated brain tissue images. It's difficult to obtain a large amount of annotated images, because annotations are the same thing as manual tracings. And again, this is very time consuming. On the other hand, it's much easier to collect unannotated images. So our goal was to leverage unannotated data by pre-training a 3D unit on an SSL or self-supervised learning task before fine-tuning this unit on the downstream 3D axon tracing task. And so in this work, we propose a new SSL task for axon tracing in particular. Our proposed SSL task is simply reconstructing the output of an edge detection method. So we have our original input image here, and then we apply the canny edge detection method to obtain the resulting image up here. We then pass in the original brain tissue volume into an encoder and decoder, and we learn to reconstruct the output of the edge detection method through L2 loss. So this is simply the SSL task component. So the overall training pipeline is as follows. We first perform SSL pre-training on the task we just discussed, and then afterwards we initialize the encoder using the resulting weights, and then we fine-tune the model on the axon segmentation component. There have been other SSL tasks that have been explored for axon tracing, and specifically it's called slice-permutation classification. The idea is you have your original brain tissue volume, and then you divide it into evenly sized slices along the z-axis. You then apply a randomly chosen permutation to those slices to shuffle them around, and then you train an encoder and auxiliary classifier to classify which permutation was applied to these slices. And this is trained on cross-entropy loss. Another related SSL task is called planar Rubik's Cube. Now, there hasn't been any previous work that we know of investigating this SSL task for axon tracing in particular, but again, it's very closely related to the slice permutation task, so we decided to investigate this as well for our work. The idea is you have your brain tissue volume again, and now you divide it into evenly sized subvolumes. You then apply some randomly chosen permutation to those subvolumes and train an encoder and auxiliary classifier to determine which permutation was applied to the subvolumes. So in our experiments, we wanted to investigate how effective each of these SSL tasks were for improving axon tracing performance. And so we have 3 different types of models, each of them SSL pre-trained on each of the tasks, and then a 4th model where there was no SSL pre-training involved. And we call this one simply the baseline model. For all axon tracing training, we used CL dice loss, and this loss has 2 hyperparameters that the user has to manually set. The first one is alpha, which is just the weighting parameter between the 2 terms. And then the second one is called K, which is the number of iterations needed to calculate this soft CL dice metric. To evaluate each of the 4 different models on the axon tracing task, we looked at 3 different metrics called dice, CL dice, and row dice. And these measure the segmentation, topology preservation, and centerline detection performances, respectively. We used 2 different datasets. The first one we only used for self-supervised learning training. And then the second dataset we only used for axon tracing training and testing. And both of these datasets are brain tissue volumes from mice. One component we wanted to investigate is how the input size we used during SSL training impacted the downstream performance. So previous work has shown that the slice SSL unit, its benefits are greatly maximized when the SSL input size is larger than the input size used during downstream training. And so we wanted to investigate if this condition needs to be true for the other SSL pre-trained units instead. And so in all of our experiments, we used 2 different types of input sizes during SSL training, a smaller and larger one. And then our input size for axon tracing training was the same as the smaller SSL size. We only include results for the smaller SSL size in this presentation for the sake of time. Secondly, we wanted to investigate how the hyperparameters in the CL dice loss impact downstream performance as well. So as a reminder, this is what CL dice loss looks like, and these are the 2 hyperparameters. Again, previous work has shown that the slice-permutation unit, its downstream performance is quite sensitive to the choice of hyperparameters. And so again, we wanted to investigate if this was the case for the other 2 SSL pre-trained models. And so to do so, we swept through both hyperparameters while keeping the other one fixed. For example, we swept through different values of k while keeping alpha fixed, and then we swept through different values of alpha while keeping k fixed. And so for each alpha k pair that we used, we conducted 10 training instances or 10 trials, and then all of our following results, we recorded the resulting metrics on the test sets. So these are the results for sweeping through k using the smaller SSL size. And as you can see, our edge unit achieved the highest metrics out of all the models for each value of k. And out of all the SSL pre-trained models, it's the only one that performed better than the baseline model on average. Here are some examples of segmentation predictions for each of the models. And as you can see in these white box regions, the edge unit seems to have predicted the most continuous connections between axons out of all the models shown. And here are some examples of centerline detections. The green lines indicate true positives, the blue lines indicate false negatives, and the reds indicate false positives. And if you look closely in the white box regions again, you may see that the edge unit has fewer false negatives than the other models. And here are some more quantitative results on the sweep through alpha while keeping k fixed, and again using the smaller SSL input size. And again, as you can see, our proposed edge unit always achieved the highest metrics. And once again, it was the only SSL pre-trained model that could outperform the baseline model on average. And finally, here are some results on how sensitive each of the models are to the different hyperparameters. And so the entries in this table are the standard deviations of the mean metrics across the different hyperparameters. For example, this top right subtable here, we took the mean values across alpha and then computed the standard deviations of them. And so a lower standard deviation would indicate that the model is less sensitive or more robust to the choice of hyperparameters. And so out of all the SSL pre-trained models, it seems like the edge unit was generally the most robust to the choices of both alpha and k. Overall, axon tracing manually is impractical, especially for large-scale datasets. And so people have looked to use 3D units to perform automatic axon tracing. And it's much easier to collect unannotated data than it is to collect annotated images. And so we wish to use self-supervised learning to leverage this unannotated data to help us in this downstream axon tracing task. And in our work, we proposed an edge detection reconstruction SSL task, and we empirically showed that the resulting downstream performances of a UNet pre-trained on this proposed task achieved the highest metrics compared to UNets that were pre-trained on other SSL tasks. And thank you everyone for watching. Hope you enjoyed it.